Hello and welcome to this video about complex numbers. And today we'll take a look at them in ways you've never seen before, and not just one, but several. And in fact, we'll start with the algebraic form of a complex number, the usual a plus ib. But then we'll see complex numbers in a very different perspective. In fact, they seem to behave like matrices and linear transformations. In particular, they can be seen as vectors and I as a matrix. Then we'll see why complex numbers can be viewed as vectors with a fancy product. In fact, this is probably the most rigorous approach. And then we'll see the difference between the complex plane, the complex numbers, and the two-dimensional vector space R squared. So if you're interested in this video and the usual a plus ib seen in very different ways, I think it's time to begin. So the first question is, what is a complex number in the first place? Well, we'll see it in a second. A complex number is made of two different parts, or better, three different things, an a, b, and I. A and b are two real numbers. But what is I? Well, I is another number, and it is a number which has the property that I times I, meaning I squared, equals to minus 1. Now the question is there a number we already know that has this property? Well, let's consider all the numbers we know. The first group of numbers we know are the natural numbers, meaning all the positive integers and 0. And we can represent them on a number line. Now, this set is called the set n of integers, positive integers. But we also have something else. In fact, we have the set of positive and negative integers, and this is called the set of integers, and its name is z. Now we can go beyond integers and start filling the gaps in between those numbers by taking two integers, n and m. If we take those two integers and we do something to them, we take their ratio, we get a number, a fraction that belongs to the set Q, the set of rational numbers. And this contains all the integers and these decimal numbers. Well, we can go even beyond Q. In fact, you may know some numbers such as the square root of 2e and pi. Those are irrational numbers. And if we take all these irrational numbers and add them to the previously known numbers, we get the real number line, the real numbers. And we denote them with the letter R. Now, R is the most extended number set we know. So we'll try to find this number I that squared equals to minus 1 in this set. So what we can do is to take our number line containing all the numbers R, and we draw another number line perpendicular to the first one, and this contains all the numbers squared. So we're basically finding all the numbers squared, and this orange curve represents all the numbers squared. And as you can see, if we go to the left of the origin, we have negative numbers. To the right of the origin, instead, we have positive numbers, and these are the input numbers. Their squares belong to the y-axis. So if we go down, we have negative numbers, and if we go up instead, we have positive numbers. And as you can clearly see from the graph, the region underneath the graph, so the region where we have negative numbers, is empty. So there is no such number squared. There is no such real number squared that gives us negative 1. So I is really something new. So we can represent complex numbers in a plane called complex plane. On the x-axis, we put the usual real numbers, and on the y-axis, we put the so-called imaginary numbers. Those are real numbers multiplied by I, and this is called the complex plane. Now, the complex plane is really useful because we can picture complex numbers as points in these planes. So this point 2 plus I, 1i, is a complex. We can also draw another complex number, minus 3 plus 2i, and if we sum the two using the usual rules for addition, we get, so component by component, we get a third complex number. But we can also represent these complex numbers with vectors, starting from the origin and pointing to the number itself. This way, addition, or the addition of these two numbers, is equal to the addition between vectors. So the addition of the two yellow vectors is the third purple vector. Another interesting thing to note is the product of I and a complex number. If we take this complex number, the previous complex number, and we multiply it by I, we get another complex number. So starting from 2 plus 1i, we get minus 3 plus 2i. And it's not clear yet, but if we draw its vector, we see that those two vectors are perpendicular. Is it true for any complex number? And yes, the answer is this is true for any complex number, and we'll prove it in a second. And finally, we want to prove that this is true for any complex number z. So if we have a complex number z, we multiply z by I, we get another vector of the same length, rotated by 90 degrees counterclockwise. So we want to prove this being true for any vector. So let's take the most general complex number, a plus ib, where a and b are real numbers, and we want to multiply this by I. So we put I in front, and this is a simple multiplication, so let's multiply the first two terms. So this is IA plus I times I is I squared b. Now, we have to take a closer look at this I squared. We know that I squared equals to minus 1, so this equals to IA minus b, and this is the second complex number, I times z. Now, how can we know if these two complex numbers are perpendicular? Okay, but we can't say whether these two are perpendicular based on the numbers themselves. We need something else, and for that we need vectors. So we can sort of identify the first complex number with the vector having x coordinate a and y coordinate b, and we can identify the second complex numbers having x coordinate, so the real component of the complex number, which is minus b, and the y component, which is a. Now, two vectors are perpendicular, meaning they form a 90-degree angle if the dot product of the two is equal to 0. So let's see if these two vectors, if the dot product of these two vectors is 0. So a, b, dot product minus b, a, equals to, we first multiply the first component of the two, so this is minus ab, we put the minus sign in front, and then we had the product of the second component, so this is plus ab, and the two terms are equal, but they have opposite sign, so we can cancel them out, and we get 0. Indeed, the two complex numbers are perpendicular. Now it's time to dive in the second chapter of this video, because we saw that complex numbers can be identified as points in a two-dimensional plane, and every point in a two-dimensional grid can be specified using a vector. And we saw that multiplying by I rotates these complex numbers by 90 degrees. So maybe we can translate this behavior into linear algebra notation, and we'll do it now. So let's start. Firstly, we can identify every complex number using a vector. So this complex number a plus ib is identified with the vector ab. And we have to find what I is in this language. I does something to the vector. It rotates the vector by 90 degrees. So maybe I is a matrix, because matrices are the element in linear algebra that move vectors around. They're transformed vectors. So I can be a matrix, and we have to find this matrix. So we saw that I times AB gives us the vector having coordinates. Well, if we do the product again, we get B minus A. Sorry, A minus B. This is the vector we get when we multiply any vector by I, because I squared equals -1, so the B coordinates gets a minus sign, and it is now the X coordinate, because it is not an imaginary number, and A simply gets multiplied by I, so it becomes the Y coordinate in this case. So we need to find this matrix. Now, every matrix, what a matrix does is simply to tell where the vectors will land after the transformation. In particular, any vector in the plane can be traced down to the sum of two fundamental vectors, the x hat vector and the y hat vector. These are unit vectors lying along the x-axis and y-axis, and they have coordinates 1, 0 for the x vector and 0, 1 for the y hat vector. Because if we stretch or contract those two vectors, meaning scaling them, and we add them together, we can get every vector in the plane. And what a matrix does is to simply tell where the x vector and y vector will land after the transformation. So, in particular, the first column of the matrix tells us where the x hat vector will land, and maybe we can use different colors. So y hat, can draw it, we can write it using the red marker. And the second column tells us the coordinates of y hat after the transformation. So this is for y hat, and this is for the vector x hat. So if we were to find a transformation that really does nothing to the vector, so we're not talking about I, we're talking about a transformation that really does nothing, meaning that it leaves these two vectors unchanged, and we can call it the matrix version of one, the identity matrix. We have to find its coordinates. So x remains unchanged, meaning it remains 1, 0, and y remains 0, 1. So this matrix, if this matrix is multiplied by a vector, or better, vector is multiplied by this matrix, it remains unchanged because we're not changing anything. Instead, we're interested in I. I does something, it rotates by 90 degrees. So let's see where those two vectors will land after a 90 degrees rotation. So if we take x hat and we rotate it by 90 degrees, it really becomes y hat. So it has coordinates 0, 1, 0, 1. Instead, the y vector, if we rotate it by 90 degrees, we get the following vector, which has coordinates -1, 0. So we can write it here, -1, 0. So this matrix rotates vectors by 90 degrees. And this is in fact I in this view of complex numbers. Why is this matrix here? The matrix 0, 1, -1, 0. And let's see whether this approach really works. Now, we won't go through matrix a vector multiplication and matrix-matrix multiplication. We just want to look at it from a simpler view. So instead of just giving you the rules of this multiplication, it is basically defined so as to this approach works, meaning that this represents the coordinates of this vector after the transformation, and those two coordinates represent the coordinates of the y vector after the transformation, and then the product is defined such that all of this is true and works out nicely. But let's see whether I squared is really -1, because that is the fundamental property of I. Well, what if we apply this transformation twice? So this is the y vector, this is the x vector. Let's apply the transformation once, rotate this thing by 90 degrees, and this becomes x hat, and this becomes y hat. If we do it another time and take these two green vectors and rotate them by 90 degrees, y hat lands here, and x hat takes the place of y hat. So if we apply I twice, meaning I times I, so I squared, we have the following matrix. First, let's find the x coordinate, the x hat vector coordinates. The x coordinate is -1, the y coordinate is 0, and for y, the x coordinate is 0 and the y coordinate is -1. Okay, so we have this matrix, but we can also factor out the -1 because it multiplies every element in the matrix, and of course it does nothing to 0. So we can write it the following way, -1 0 0 1. But this is exactly the starting point, 1 0 0 1. In fact, this is the identity matrix. So I squared is minus the identity matrix, which is the one version of matrices. So it really all works out nicely. The only problem with this approach is that I is not a complex number, because complex numbers are vectors, and in this case, even though sort of everything works, I, in this case, is not a complex number. It's something that does something to complex numbers, but it isn't really a complex number. And if you look at the grid, at the complex plane earlier, you found that this number was 1i, meaning I, but and has coordinates 0 1. But 0 1 is not I in this case. It is something else. This is a complex number. This is not a complex number. So this is the major problem with this approach. And there's also another problem, because this one is not 1. I mean, by 1 we mean the vector 1 0. This vector represents 1, but this is not equal to this matrix here, 1 0 0 1. They are two different things. So even though it resembles the behavior of complex numbers, this is not these are not real complex numbers. And this leads to the next approach. And this is probably the most rigorous one. So let's start. Now it's time for the final approach. And yes, complex numbers are still vectors, but somewhat different from what we've seen until now. And yes, we start with they are vectors in the first place, meaning they are elements of R squared, meaning the set of all two-dimensional vectors. And they have an addition rule and a product rule. Now, addition is the same as vectors. We've seen it earlier, and we'll see now again. But the product is somewhat different, and it's what differs complex numbers from the simple vector space R squared. because this is a field, complex numbers are a field, and we'll see in a moment what that means. So let's start. Firstly, if we have two complex numbers, there is a rule of addition. If we take two complex numbers, let's say a plus ib plus the second complex number, and let me use another color, plus sorry, not A, let's use C plus ID. We can add them up together and we get this equals 2. We sum those two, the real parts. So A plus C, it's the new real part plus the imaginary part. So we have I times, we basically factoring out the I, so B plus D. And we basically applying the usual rules of addition and multiplication, so there is nothing new really. We're basically using the properties of real numbers with complex numbers. So if we have two complex numbers, now I'm using row vectors, but it's the same thing, A and B plus C, D, we can add the component. So this is the rule for addition, A plus C and B plus D. Now there's also a rule of multiplication, and this is probably the most interesting of the two, because if we take two complex numbers, say A plus IB times another complex number, let me use another color, C plus ID, and we multiply them together, we multiply the two. Let's follow the rules of real numbers, but we have this I here. So this is A, let me put the I in front, let's start with C. So AC plus IAD plus IBC plus I squared, because I times I is I squared, BD. Now, recall that I squared is minus 1, so this term becomes minus BD. And we can take together, we can basically add the two real components, because this has become a real component. So this is AC minus BD, and this is the real part of the complex number, plus I times AD plus BC. So this rule is not straightforward. It is if we use the multiplication rules, the usual multiplication rules, as we've done, and we derived this formula. So if I have to erase the first part because we don't need it now, if we have AB times CD, this equals to AC minus BD, AD plus BC. This is the rule for multiplying two complex numbers, and you see this is not the usual vector product. This is something new that only belongs to complex numbers. Now, this is a field because those two, both the addition and multiplication, those two operations, follow the usual rules, basically. This is put simply. We should go into detail and take a look at those, but it's boring and we won't do it in this video. But simply because those two behaves like the addition and multiplication rules behave as it is for real numbers, integers and all of that, they are numbers. This is a field, this is not a vector field. So this is the most important thing to bear in mind. And let's take a look at what is I in this case. So we identify in the plane I as this vector here. So it has coordinates 0x and 1y. Instead, 1 has coordinates 1, 0, 1x, 0, y. Let's see whether it works. So if we take, let's say, I don't know, let me switch colors. If we take any real number, and we can identify real numbers using complex numbers, we will come back to this in a second. For example, the number 50 is identified with the number. Okay, my mobile turned off, but it's time to continue. So we were looking at 50, why this is equal to 5. Well, because there is a bijection. It's called a bijection between 50 and 5, meaning that they share the same properties, and sharing the same properties, they are the same thing, with just different notation. So, for instance, if we take 50 and we add to it the number 60, we can follow this rule: a plus c, 5 plus 6 is 11, 0 plus 0 is 0, so this is 11, and it resembles the operation, the addition among real numbers. We can also try multiplication: 50 this time times 60, and we can follow the same rule. So AC minus BD, AC minus BD, so AC is 30, 0 times 0 is 0. Again, we get a real number. So there is a bijection between normal convention, standard convention of real numbers, and these two numbers, this new object, this vector. So they are the same, just two different notations. What is interesting though is that if we take a look at the previous graph, we will notice that I instead is a complex number this time. Of course it is. And by I, we mean the number, this number, so it has coordinates 0, 1. Let me use a row vector, 0, 1. So 0x, 1, y. And let's see that if we take, for example, 50, this is 50, and we multiply by I, we get the same vector rotated by 90 degrees, same length, I mean. So we get 0, 5. Let's see whether this is true. So 50 times 0, 1, this should be 0, 5. Let's use this rule. So AC minus BD, AC, 5 times 0 minus 0 times 1, AD, so 5 times 1 plus 0 times 0. So this is 0, and this is 5 times 1 is 5. So see, we get 0, 5. And even if we exchange 50 and 0, 1, we always get the same thing. So this is why this approach works. We can also try I squared. Let's try I squared, if you're not convinced yet. I squared, so 0, 1 times 0, 1. Let's follow the same rule. This is AC, AC 0 times 0, minus BD, 1 times 1, and then A times D, it's 0 times 1, which is 0, plus BC, so 0 again, 1 times 0 is 0. So this is minus 1, 0, and this is identified with the number minus 1. So everything works out nicely, and thanks for watching this video. If you enjoyed it, leave a comment down below, share this video with your friends, don't forget to subscribe to my channel, and see you in the next video. Bye.